Hello everyone, welcome back to Introduction to Number Theory. In this short video, we will discuss the notion of a Euclidean ring. First, take a good ring. What do we mean by a good ring? Well, it's an associative, commutative, integral ring with a multiplicative identity. Associative, according to the multiplication, of course. Commutative also is about multiplication. Integral means that no two non-zero elements can have product equal to zero. And having multiplicative identity means that there is an element denoted usually by digit 1, such that this element multiplied by any other element results in this other element. This is the cause why we will often use word unity, not identity, because we really denote it as digit 1. Okay, so now we have a good ring. And in order to have a Euclidean ring, we need to introduce a norm, definition of a norm. And norm of a Euclidean ring, future Euclidean ring, is a function from all non-zero elements of the ring M into the set of non-negative integers. And actually the only condition on this function we need to hold is that the norm of a product is not less than the norm of each of the factors. Well, it is not a usual norm, but it is what we need to define a Euclidean ring. Okay, now when we know what a norm is, we can define the Euclidean ring. By definition, a good ring is called Euclidean if there exists a norm such that there is division with remainder with respect to this norm. Division with remainder. As usual, this means that for any two elements A and B, there should exist elements Q and R. Note that we do not need these elements Q and R to be unique. They only need to exist, such that A is equal to BQ plus R, and R is, well, less than B. So we need the norm to say what less means. R should be either 0 or have norm less than norm of B. Well, these are the definitions, and do we encounter Euclidean rings during our math practices? Of course we do. So here there are some examples of Euclidean rings. Well, just a ring of integers with absolute value as the norm. It is a well-known Euclidean ring, and it is well known that there is division with remainder in the set of integers. And the ring of polynomials over a field, and norm in this ring is the degree of a polynomial. And it is also well known that there is a division with remainder among polynomials. And the third example is the set of complex integers, or so-called Gaussian numbers. It will be discussed in the next fragment. And here you go, several examples of non-Euclidean rings. Well, for instance, the ring of remainders modulo 12, remainders when divided by 12, with arithmetics also modulo 12, which means that if we add two remainders, then we need to get the remainder of this sum, and the same with multiplication. I believe that this is also a well-known ring. However, it is not Euclidean, and it is an exercise for you to prove this. And another non-Euclidean ring, the ring of complex numbers of the form integer plus integer multiplied by I square root of 5. standard notation for such ring is z of I square root of 5. And standard operations of sum and multiplication. And also I leave it as an exercise to prove that this ring is not Euclidean. However, this is a more difficult question, and maybe you should wait for the end of the next week in order to have enough facts and theorems that will help you prove that this ring is not Euclidean. So we see that there are Euclidean rings and there are non-Euclidean rings. And of course, we will mostly deal with Euclidean rings in number theory, because in Euclidean rings, as we will soon see, we will have the uniqueness of factorization, the linear representation of the greatest common divisor, and many other pleasant things, pleasant properties of these rings.